Welcome to the Explainer. Okay, let's talk radar. You ever wonder how we can track a plane that's miles and miles away, even when it's pitch black or super foggy? Well, today we're going to break it all down. We're going to build a radar system right from scratch, piece by piece. So hey, if you're just getting into this stuff, or maybe you're cramming for an exam, you are definitely in the right spot.
So let's just start with the core problem, right? The whole reason radar even exists. Picture this. You've got to find something that's way, way out there, but you can't see it. Maybe it's foggy, maybe it's the middle of the night. What do?
Yep, that's it. You use an echo. It's just like shouting into a big canyon, you know? You listen for that echo to come back, and that tells you how far away the other side is. Radar does the exact same thing, but instead of your voice, it sends out a pulse of radio energy. And then it listens for what bounces back. But how does a machine actually pull that off? I mean, how does it create a shout that's powerful enough to travel for miles? Listen for an echo that's barely a whisper and somehow not deafen itself in the process. That's the real trick.
To figure that out, we've got to look at the four major subsystems that make up pretty much any radar. Think of them like a little team, and each member has a super important job. We've got the synchronizer, the transmitter, the duplexer, and the receiver. Let's dig in and see how they all work together to make the magic happen.
Okay, so here's our roadmap. First, we'll check out the system's heartbeat. Then we'll talk about its powerful voice. After that, we'll get into the smart switch that makes sure everything goes to the right place. And finally, we'll cover the super sensitive ears that listen for that faint echo. All right, first up, the synchronizer. And that subtitle, The System Heartbeat, is just perfect. It's basically the master clock, or the pacemaker for the entire system, making sure everything happens exactly when it's supposed to. So its official job is to create these things called trigger pulses. That's what the source material calls them. And a great way to think about it is like it's the starting gun at a track meet. It fires off and tells every other component, okay, go! It's time to do your thing right now. And why does this matter so much? Well, because for radar, timing is everything. Literally everything. The whole system figures out how far away something is by measuring the time it takes for that echo to come back. So if the timing is off, even by a tiny fraction of a second, your distance calculation is going to be totally wrong. The synchronizer is the one component that prevents all that chaos and keeps things precise. Okay, so we've got our heartbeat, our timing is locked in. Now the system needs a voice, a really, really loud one. As soon as the synchronizer fires off that trigger pulse, something has to generate that powerful shout that goes out into the world. And that's where the transmitter comes in.
So the transmitter is listening for that signal from the synchronizer. The second it gets it, bam, it creates the actual radio wave. Our source material says its job is to produce these short, really high-power pulses of radio frequency energy, RF energy, that then get blasted out by the antenna.
So why the big deal about high power? Well, it goes right back to our canyon analogy. The louder you shout, the farther your voice travels, and the stronger the echo is when it comes back. It's the same thing here. A more powerful transmitter means the radar shout can go way farther out, so it can see things at a much greater distance.
And a classic example of this, what you're seeing right here, is a device called a magnetron. A lot of transmitters use these. It's this special type of oscillator that's just incredibly good at generating the super high-power microwave pulses you need to get that long-range detection.
Okay, so let's pause for a second. We've got this super powerful transmitter, our voice, and we're going to need a really sensitive receiver, our ears, and they both need to use the same antenna. See the problem? How do you let the system shout with all its might and then listen for a tiny whisper using the same antenna, without that massive shout just completely frying the sensitive listener?
Well, the solution is actually pretty brilliant. It's called the duplexer. You can think of it as a really, really smart, high-speed switch. Its whole job is to manage the traffic. It connects the antenna to the transmitter for that brief moment of the shout and then instantly switches it over to the receiver to listen for the echo.
And I can't stress this enough. This thing is absolutely crucial. That pulse from the transmitter it's millions of times more powerful than the tiny echo the receiver is trying to hear. Without the duplexer acting as a bodyguard, that massive power surge would hit the receiver and poof, its delicate circuits would be toast, instantly.
And this is a great way to see how it works. Look here on the left, in transmit mode. The radar is shouting. The duplexer connects the transmitter to the antenna and basically slams the door shut on the receiver. Then, a microsecond later, look at the right. Now it's in receive mode, or listening mode. The duplexer completely disconnects the transmitter and opens up a clear path from the antenna right to the receiver.
All right,
So let's follow the signal. The pulse went out, it hit a target, and a tiny, faint echo has traveled all the way back. It's hit our antenna, and the duplexer has done its job, protecting the system and routing that little echo to the right place. So now what? Now we actually have to hear it and make sense of it. And that, of course, is the job of the receiver.
The receiver is the system's sensitive ears. And when I say sensitive, I mean it. Its job is to pick up an unbelievably weak signal. We're talking a signal so small it's measured in microvolts, and then amplify it millions of times so it's strong enough for us to actually use, all while trying to ignore all the other random radio noise out there. It's a huge challenge.
This is a really important point. If the transmitter's power determines the maximum distance the radar can reach, then the receiver's sensitivity determines the minimum signal it can detect. It's what lets you see small things or things that are really far away. A good receiver is the difference between spotting, say, a tiny drone from miles away or it flying by completely unnoticed.
Now check this out. This diagram shows a really common type of receiver, called a superheterodyne receiver, and it has a really clever trick up its sleeve. See, trying to amplify a really high-frequency signal is tough and can be noisy. So instead, this receiver uses a component called a mixer to first convert the incoming echo down to a lower, much more manageable frequency. They call this the intermediate frequency, or IF. Then, it's super easy and stable to amplify that IF signal. It's a total game changer for getting a clean, strong signal from a faint echo.
And that's it. We've just built a basic radar system from the ground up. We've got the synchronizer, our heartbeat, the transmitter, our powerful voice, the duplexer, the smart switch, and the receiver, our sensitive ears. Now, to make sure all this stuff really sticks, especially if you have an exam coming up, let's do a quick recap and then hit some practice questions.
Okay, let's do this fast. Rapid-fire recap. The synchronizer? That's the system's master clock, the heart. The transmitter? That's the powerful voice, generating the pulse. A magnetron is a common part that does that. The duplexer? That's the smart switch, protecting the receiver. And the receiver? Those are the sensitive ears, detecting the echo. And that special type, the superheterodyne, uses that intermediate frequency trick. Got it? Good. Let's see what you know.
All right, first question for you. Which component do we call the heart of the radar system, the one that controls all the timing for everybody else? Think about it. Yep, it's the synchronizer. That's the one sending out the trigger pulses. Okay, next one. What is the main, number one purpose of the duplexer? Its most important job is to protect that super-sensitive receiver from getting blasted by the high-power transmitter. That's job one.
And last question here. In that superheterodyne receiver we looked at, what stage is doing most of the heavy lifting, most of the signal amplification? The answer is the IF amplifier. That's where the big gains happen, but only after the mixer has stepped the frequency down. So, as we wrap up, think about this. These subsystems are the building blocks. But how do you think engineers today balance the push for an even more powerful voice with the need to build even more sensitive ears to hear fainter and fainter signals? That's really the puzzle they're always trying to solve.